Cool. So what we had gotten to last time was we had defined pre-sheaves. So this was an assignment of every open inside some topological space X to a set, or more generally, object in a category, which we called F of U. So the pre-sheaf itself would be called F, and I have this assignment to open sets such that when I have an inclusion, so I have U and then I have a bigger open set V, I get a restriction map from V to U. So the rough idea is this would be some kind of functions which are specified by some kind of local condition, so that when I restrict, it would make sense to restrict them to a smaller open subset and they would satisfy the same conditions. And I require a transitivity here of, if I had a bigger open subset W, I could start on W and either do it in 2 steps or 1 step, and I would get the same answer. And apparently also I have to say that if I restrict from U to itself, that gives me the identity. And as I mentioned, you can think of this as a functor from a category of open sets, where the morphisms are the opposites of inclusion. So it's the opposite of the usual open set category. And this is saying that when you have a functor, it has to send identity morphisms to identity morphisms. All right. So those are pre-sheaves. But in this course, we're mostly going to talk about sheaves, which are going to sound briefly like some sort of very subtle, come on, wouldn't you expect that condition anyway, sort of thing. And then we're going to see they actually make a significant difference. So a sheaf is a special type of pre-sheaf. So let me say a sheaf is a pre-sheaf. And let me for now talk about sets. So pre-sheaves, it makes perfectly good sense to talk about in any kind of category, right? I could take this to be an object in any category and just say whenever I have a restriction, I have a morphism. And I only use the notion of composition, so everything is fine. So for now, let me talk about a pre-sheaf of sets. Usually we'll be talking about pre-sheaves of sets with extra structure. So sheaves of abelian groups are very popular, and we'll also think about abelian groups with yet more structures, which we haven't talked about yet. But that's the kind of thing you should think about, is either sets or abelian groups. So it's a pre-sheaf, and it has to satisfy 2 additional conditions, which Bacchiel calls identity, which basically says if you can check that 2 sections of the pre-sheaf are the same locally. So if I write my open set as a union of smaller open sets UI, and just following my notes. So I'll often write this bar and then sub UI to mean res UUI of F1, which is kind of easier to write it that way. So I have an open cover, and I have 2 sections on the union. And on every open set of this open cover, they're the same. Then F1 equals F2. Okay, so this is a very, very natural thing to ask for, but it's not in the definition of pre-sheaf. It's maybe worth noting here, the definition of pre-sheaf uses nothing about the notion of intersection or union of open sets. It only uses the data of which open set is contained inside which one. So it's only once I go to sheaves that I'm incorporating this extra information of when I take the intersection of two open sets, which open set do I get? Or take the union. In this case, I'm using the union. So, I mean, this sort of sounds like, well, come on, like, wouldn't you always have that property? But on X, there's a perfectly good pre-sheaf, F, which I define to be any set I want, U when my U is the whole space, and the empty set otherwise. Let me do a one-out-one set. Sorry. So I can take some huge set for the whole space, and for any proper subset, I have the one element set. And I have to tell you what the restrictions are. So the restrictions are either everything goes to the 1 point, or 1 point goes to 1 point. So this is a perfectly good free sheaf, but it's obviously not a sheaf, right? Any two elements of Y, when I restrict them to any open cover that doesn't contain the whole thing, I'm always going to get the same elements. So this is the kind of dumb stuff you can do if you're thinking about pre-sheaves that we don't want to allow when we take sheaves. All right, so this sort of says something about comparing things. The other property is about the existence of sections. So gluability. So I said sort of sheaves are about things which are defined by local properties. So this says I can check equality locally. The other one says I can sort of check existence locally. So similarly, if I have U and I write it as a union of open sets, and there exists Fi in F UI, such that when I look at the overlap, so I restrict Fi to one of these intersections, and it agrees with Fj on the same intersection. So this equality is happening in F of Ui intersect Uj. So what is this saying? I have a bunch of open sets. I have some kind of function type thing. And whenever I restrict it to overlaps, it agrees. Then there exists a unique F in the sections of U such that when I restrict F to Ui, I get my Fi. Yeah. Yes. I only need existence here. It's unique because if I already know the identity property, then they have to be two things satisfying this property would have to be. Yeah. All right. So what's an example of a natural pre-sheaf that doesn't satisfy this? I mean, if you think about the dumb examples you can cook up here, there are plenty of them. Actually, this one is okay. Right? I can take an open cover. The only thing I can do is take the 1 point thing every time. And indeed, it's very easy to pick a guy on the whole set that restricts to that everywhere. It doesn't satisfy the uniqueness because the identity thing doesn't hold. So a pretty important example of a pre-sheaf is what we call the constant sheaf. We put all this sort of horrible notation on here. What does this mean? This is the pre-sheaf on X such that if I apply this to any open subset, I get Y. So this is for Y some set. All right, so that's a perfectly good pre-sheaf. I just take all the restriction functors to be the identity map from Y to itself. All right, but I'm obviously going to end up with a problem when I have two open subsets which are disjoint from each other, right? So on here, I have a section y1 in f of u1. In here, I have a section, oh, I made a mistake here. I have to let y of the empty set be the one element set. My example isn't gonna work. So I should say here, right, from any guy, I have a restriction functor to the empty set. So the natural thing to put for the empty set is the terminal object in your category. And I think we were having a discussion about whether you want to require that for pre-sheaves or not. But we definitely want to require that for sheaves. That'll be kind of forced on us by the sheaf properties. Okay. So why is this important? Because this means that if I look at y1 restricted to the intersection of these guys, that's the empty set. So it's the unique element of my one element set, and that's the same as the restriction of y2. Hmm? If f of the empty set were still y, then this would be requiring that y1 and y2 are equal. Right? I'm trying to break this sheaf condition. So I want to come up with two local sections that agree on the overlap, but which don't glue to a global section or don't glue to a section on the union. And I need to have this property to fix. Like, I need to have that the intersection is something different from these guys. Yeah, the only thing I need here is that these guys are mapping to the same element of f of the intersection. So there are lots of other examples you could come up with. This is just kind of a natural one to try to see what's going on here. Okay, great. So I have a problem here. If y1 and y2 are not equal, then there doesn't exist an element of y, which is the f applied to u1 union u2, such that y restricted to u1 is y1, y restricted to u2 is y2. The point is just constant functions don't glue, right? Because they can have different constant values on two disjoint open subsets. Right, this might look a little strange when I write it this way. I probably should have written f of u equals constant functions from u to y. And the reason is, well, if u has any points in it, then I just associate this to the image of any one of those points, and that gives me y, because all the other points have to map to the same place. But if I look at the empty set, there's only one function from the empty set to y, which just doesn't do anything. Right? A function is by definition a subset of the Cartesian product, and there just is the Cartesian product of the empty set with y is empty. So I take the empty subset of that empty Cartesian product, that gives me the unique function. Okay, great. And that sort of corresponds to the intuition of, indeed, when I think of these as actual functions, they do agree when I restrict them to the overlap, because there's just no overlap. Cool. So this is not a sheaf. All right, are there any questions? Okay. Let me skip that for a moment. So I've given you two examples of things which aren't sheaves. Maybe I should give some examples of things which are sheaves. So I can fix this guy by defining what we call the constant sheaf. So I have to tell you what this is assigned to an open subset. I want to take locally constant functions from U to Y. I should probably define what locally constant means, but hopefully that's relatively clear. Locally constant means for all elements of U, there exists a smaller neighborhood in V, which in U, which contains this point little u. Whoops, that for all in U, there exists a neighborhood such that is constant on V. So for example, here, the function that sends all the points in U1 to Y1 and all the points in U2 to Y2 is locally constant. So it gives me a perfectly good section of this sheaf, and my gluing condition is satisfied. All right, I should mention, all right, let me mention two things here. So I had mentioned in class last time that whenever I have a topological space E mapping to X, I can define a sheaf by looking at sections. Maps of U to Y. Let me say continuous, such that when I compose them with the projection, they become the inclusion U. So in order to get this locally constant sheaf, what I should take is E is equal to X times Y, where I give Y the discrete topology. So just think this through. What does it mean to map U into this product such that I get this property? So this just says that when I have a point here, I send it to the same point. Actually write this out. U has to map to the same thing in the first factor, and then something in the second factor. And taking the discrete topology here exactly guarantees this local constancy, right? Because I take the discrete topology, every point is its own open subset. And by continuity, the preimage of that point is an open set. Or I should just say contains a neighborhood. Yes, right. In this case, E is X times Y. Oh, sorry. Yeah. U to E. Yes, sorry. So in general, sort of one of the ways of kind of fixing this pre-sheaf thing is to always come up with a space like this. And since these guys are defined by actual continuous function, this will always be a sheaf. All right, another pretty important example is what's called skyscraper sheaves. Which I'll denote sky P Y. So this is the sheaf. Whenever I tell you sheaf, I have to tell you what it assigns to an open subset. So this assigns to Y to any u containing p. This is for a, y a set, some fixed p and x. And the one element subset if p is not in u. So I should tell you, how do I, here it was sort of obvious how to make this into a sheaf. I just literally restrict the functions. Here, right, whenever I pass to a smaller open subset, well, I can only go from having p to not having p, right? I can't go from not having p to having p. So my restriction maps are either the identity on y, the identity on this guy, if I don't, if neither of these had p, and if I had p and then I lose it, this just becomes the unique map that sends all the elements of y to the same guy. So you can also think of this in terms of maps, though the space is weirder. What the space looks like is, here I have x, I remove the point p, and I replace it with a copy of y. And I'll leave it to you guys to figure out what the right topology on this one is. It's kind of weird. It's not Hausdorff. But it's called the skyscraper sheaf because this copy of y kind of looks like a skyscraper jumping out of this point at x. And the way I think of this as a function is, at every point other than p, I just have to stay in the same spot. And then at p, I map p to one of the elements of this image. And I have to set things up so that I could map to any one of them, which is why it's a weird topology. All right. Any other questions? Yeah. See. Sure. But no, because varieties can be disconnected, right? Or actually not even necessarily disconnected, just not irreducible, right? If you have a non-irreducible, some people like to define variety to mean irreducible, but you can have a non-irreducible algebraic subset of Cn, right? And then there can be disjoint open subsets of two different components. That's true, yes.
Could you please repeat the questions?
But, oh yeah. Okay, well, yeah. So I would say if you're online and you want to ask a question, probably it's better if you raise your hand. So then we'll know that you actually want to raise a question. So yeah, please use the raising hand feature. So you shouldn't only think about the Zariski topology, right? We're mostly going to be working with the Zariski topology on schemes in this course, but these notions still make sense in other categories. So for example, I might take X to be a smooth manifold. And there's a sheaf on here called C infinity, where C infinity of U is the smooth functions from U to R, or if you wanted to, you could say smooth functions to C. Just depends how you're feeling that day. Right, and you can also consider in this context, there's a sheaf of vector fields. There's a sheaf of 1 forms, or more generally K forms, etc. So you shouldn't discard a notion because it isn't interesting in the Zariski topology. And even in the algebraic world, so one of the buzzwords that would come up if you read about the Weil conjectures that we won't really have time to talk about here is there's this notion of the étal topology on schemes, which is meant to kind of behave more like a manifold topology than the Zariski topology. All right. Okay, one more example of how to cook up sheaves, because it's kind of important, well, for things we'll do throughout the course. Assume T from X to X prime is a continuous map. Then given F a sheaf, or I could also say pre-sheaf, but let's talk about sheaves. Sheaf on X, I can define a push forward sheaf. So one thing you very frequently want to do with these kind of objects is consider how can I move them around from one topological space to another, right? We always want to think about categories. So we want to think about the fact that there isn't just one topological space sitting here. There are lots of topological spaces around. Is denoted P lower star of F. So I have to tell you what this is on an open subset, and this is going to be a sheaf on U X prime. So I have to tell you what this is on U, a subset of X prime. And how can I take a subset of X prime and make a subset of X? Well, there's one reasonable way to do it, which is I can take F of P inverse of U. Right, so this defines a sheaf on X. To see why it's a sheaf, what do you use? You use the inverse image respects union and intersection. And of course, I'm using that this is a continuous map, so the pre-image of an open set is open. All right, so this is sort of a natural way of transferring things. Forgetting now whether I introduce this notation, but I'll just, oh yeah, no, I haven't yet. So I'll talk about that in a moment. All right, are there any questions about just kind of what sheaves are? So we're going to have to talk a lot about kind of the basic notions surrounding sheaves. And one of the most basic notions is this idea of germs and stalks. So a germ of a section. So some of you might be familiar with the notion of a germ of a map. At an element X and X is a pair U, an open subset containing X, and F, an element of a section of the sheaf on this open subset U. So I have a point X, I look at a little open neighborhood around it, and I take a function defined on that open neighborhood. And I want to put an equivalence relation on these. So this is modulo the equivalence relation that I take V and restrict F to V. This is, of course, for V, a subset of U. So I declare two of these to be the same. If I can shrink U, V still has to contain X. So the way I should think about this is here I have X, and I'm taking smaller and smaller and smaller open subsets around it. and looking at sections on smaller and smaller subsets. If I look at all of the germs at a point X, those form a nice set, which we call the stalk. So stalk, so this is F sub X, and this is little x, a point in my space, is the set of all germs at X. So I look at all of the open subsets containing X, and I look at sort of progressively smaller and smaller ones, right? I can always, if I have two open subsets, I can always just look at their intersection. And so I'm taking germs on smaller and smaller and smaller open subsets.
There's a question in the chat.
Mhm.
The definition of a situation, which says that if there's a double
I mean, that's the transitive closure of this, right? So the way I wrote this relation isn't symmetric. More importantly, it isn't transitive, because indeed, yes, I could take, here's U, here's V, here's W. Well, right, this says U is equivalent to its restriction to W. It also says the function on V is equivalent to its restriction to W. So that says that these guys are equivalent there. So yeah, you want to take this relation and complete it to an equivalence relation. And then, yeah, probably a more symmetric way of saying it is saying there's an open subset of the intersection where they agree. All right, any other questions? Okay. So I'll just mention here, of course, you should, if I have any section and X is an element of U, then I can look at the germ of that section in f of X. So I have a map from f of U to the stalk f sub X. And you should think of this as some generalization of taking the value of a function. So certainly that's sort of part of how you should think about this. I mean, sheaves, as we discussed at the beginning of the course, you should think of sheaves as elements of sheaves as functions, but you shouldn't take that too literally. And one of the ways you shouldn't take that too literally is this will remember more than that. So for example, in this case, right, if I look at smooth functions, if I look at the germ of a function around a point, that doesn't just remember the value of the function. In particular, it remembers the whole Taylor series. And actually, it remembers more than that because there are lots of smooth functions that aren't analytic. But in this case, f of X, well, in particular, remembers Taylor series. Yeah, sure. Well, I mean, in this case, the stalk at a point is always one, right?
does not carry.
It could. I mean, the stocks can all be the same, or they could all be different, right? And for example, in the skyscraper case, right, the stock at every point other than P will be a one-element set. The stock at P will be your Y. That's sort of another way to think about why it's called skyscrapers. It has one big stock, and all the other stalks are boring.
Yes, question. They're asking.
Oh yeah, sorry.
So, what's that? That's-
Yeah. Yeah. Well, no, this is for one fixed X. So sorry, it's sometimes kind of hard to quickly summarize the question, but what he was saying is that, so there's also a thing you can do, which is instead of trying to think about the value at one point, think about the value at all the points. So I can think about the Cartesian product of all of these stalks and think about having a map into there. Or the product, the section maps to yeah, right. I take F and I send that to F, take the stalk at X for every X in U. The question was whether this should be a coproduct. There's also a construction that involves the coproduct meaning disjoint union, since we're talking about sets. So you can also think that there's a map from U into the disjoint union of all of these sets, which means I send U to the stalk. Oh, sorry, I said the wrong thing here. Given a section over U, then I get a map from U into here, which is send U to the stalk of F U. And this is a section of the projection map, right? There's a map down here that sends every stalk to the point that it sits over. Yeah. Mm-hmm. Yeah. Yes. So those no, those would not give me the same element of the stalk because there's no open subset on which they agree. So that's exactly, so sorry, he was asking, yeah, it's hard to summarize these questions right when I think what the person is asking is wrong. But the point is that having the same value at a point is not the same as having the same image in the stalk there. Because the stalk is remembering the germ. So it's sort of a little bit weird because it's also true that, right, you can take smooth functions that agree on some small open subset and then do completely different stuff other places. And those have the same germ. Right, so somehow I should actually double check this. I haven't thought carefully about, if I had said analytic functions here, then I could just say it remembers the Taylor series and nothing else, right? But because I said smooth functions, I genuinely haven't thought carefully about, is there extra information in the germ? Probably yes, but I don't want to absolutely swear to it. And I just, it's not something I know off the top of my head. All right. So I should mention this space is what's called the espace apal. It's mentioned briefly in Vakil, and we will probably come back to it later when we talk about sheafifications. All right, we've got 10 minutes left. Yeah.
I'm just wondering, is that an example if you had sheaves of vector spaces of as a tangent space as a vector bundle? Like
I can't hear that.
like if you considered
Okay, well, could you hear what they said?
Can you repeat the question?
Or maybe just write it.
Sheaves of vector space. Is it the vector bundle?
So not, you should think of it as a little bit like a vector bundle, but it is actually pretty different. Because exactly because of this issue, right? Like this is smooth sections of the trivial vector bundle, but you're not going to get the trivial vector bundle here. You're going to get something huge and infinite dimensional where you sort of remember the Taylor series. So, I mean, somehow what's happening here is there's a kind of more complicated topology on here. I mean, there's a way of thinking about, like, I mean, again, I should say analytic functions, just to make this a little nicer, where you can think about the vector bundle of like all possible Taylor series, and then that has a flat connection where things that actually come from analytic functions are the flat sections of that. That's more what this picture looks like. All right. So yeah, let's try to finish up on something good. Another important application. So we've been talking about sheaves, that's great, and about thinking of them as a generalization of functions. So, you know, if I told you this story in a manifolds class, I would be like, oh, well, actually, all the information in a smooth manifold structure is in this sheaf. If I tell you what the smooth functions are, I don't have to tell you an atlas. I mean, really, this is sort of a better way of thinking about smooth manifolds than atlases. So saying what kind of functions I want to think of as my basic kind of functions is kind of telling you a geometric structure on the underlying space. And the way we sort of formalize that idea is to think about what are called ring spaces. So that's a pair of a topological space, like we've been dealing with the whole course, X. And then I want to put on that a sheaf of commutative rings. And at the moment, I don't want to put any other restrictions. So that smooth manifold, that's an example of a ringed space. And I think of that kind of ring space structure as really encoding the manifold structure. This guy is usually called the structure sheaf. And since these are sort of my basic functions, everything else that appears is going to be a module over the structure sheaf. So this is sort of the world in which we're going to be working for most of the course, is thinking about ringed spaces for appropriate choices of X and O of X. Another example that might be helpful to think about, if you have a complex manifold, then you can not just think about the sheaf of smooth functions, you can think about the sheaf of holomorphic functions. All right. So once I have this, now I want to play all my sheaf games. So it's common to consider the stalks of this, O of X comma P, the stalk at P. This is called the local ring at. And I should say here, I don't actually want to assume that this is a local ring in the sense of commutative algebra. But this is where the terminology local ring came from, though probably not stated in these terms. So if this guy is local for all P, we call this a locally ringed space. And I'll leave it to you guys to, for example, check that with a smooth manifold, I actually do get a locally ranged space there. Maybe with some sort of slight care about topology. All right, and a common thing we'll want to consider is, I'll call an O of X module. Is a sheaf of abelian groups such that if I take f of u, that's a O of X of u module, right? So for every open subset, I get a commutative ring. And so I can look at sheaves, which on each open subset are a module over that commutative ring. And this is very geometrically natural. So for example, here, I can multiply a vector field by a smooth function. So vector fields are a module over this ring. It's a O of X module on this ring space. Similarly, a K form, I can multiply by a smooth function. So just about anything I want to consider in differential geometry is going to be a module over this space of smooth function. And again, sort of somehow, when you're doing differential geometry, you can get away with kind of leaving that implicit. But for us, because we want to sort of start with the ring and kind of produce the idea of functions out of that, we have to be really explicit about this stuff, about what kind of thing am I cooking up here. So you should think of these as sort of like vector bundles that are compatible with this choice of the set of functions. All right. I think that's all we have time for today. So I'll end with that. And we'll talk more next time about sheaves as a category. Are there any questions? Yeah. No. I mean, there's nothing fancy happening here. A ring is a set with extra structure. So the computation of it as a stalk is all just happening on the level of sets. Yeah, I mean, it's exactly this. Yeah. Yeah, I mean, it's so, one thing I've been skating over is you can talk about sheaves in arbitrary categories, but you then have to figure out how to write that identity and gluability condition without talking about elements of the sets, right? And similarly, you can define this stalk, but you have to say it in a different way. And in particular, you have to say the word co-limit, which in sets just means take a union. And so we can get away with this, right? There's a co-limit here, but the co-limit is just taking the union of all of these guys. So yeah, there's nothing sort of special about the category of rings here. I'm just taking a union. I mean, right? We're eventually going to be thinking about, spec of R here, right? And then as we discussed last time, they're open sets, which are take any element of R and require that to be non-zero. So like what happens when I interpret this stalk condition there? I can get this guy by just saying, I have an open subset where I invert some function and I take a section on that, which is an element of the ring divided by a power of that guy I inverted. And that's exactly the local ring. Okay, so I'll explain that in more detail when we actually talk about affine schemes, but there's nothing, the only sort of thing that's important here is if the sections, right, if f of u for all u has some additional structure, which is compatible with all the restriction maps, like being an abelian group, being a ring, etc., then you are going to want to sort of take that structure along for the ride when you take stalks. And there may be some slightly weird subtleties about like what happens with the empty set. Because, right, like if you have a sheaf of abelian groups, when for the empty set, you want the terminal object in the category. So you want the zero abelian group. Yeah. Right. But so there is a little bit of weirdness about like my usual convention for a ring would be that the zero abelian group is not a ring. But I want to kind of make an exception for that in this case. Right, that I only want to assign unital rings to non-empty sets. That's maybe the only funniness about taking the sheaf of rings.